So welcome everyone back to the second lecture for multivariable calculus. We will be talking about vectors, dot products, orthogonal projections, and cross products. Uh, while these are not strictly only for multivariable calculus, they're incredibly important tools for mathematics in general and have strong relevance in linear algebra and physics as well. Let's start off then. Let's start off with vectors. So vectors. Okay. So vectors can be defined as the shift between one point to another. You can think of this in physics terms. For example, if you have an object in some type of plane, so if I quickly draw out a plane, let's say this is the XY plane, which we're all quite familiar with, I hope. Okay. XY plane. Let's say an object starts at this point over here, and then you shift it across all the way to, let's call this P. Okay, so this shift, so this vector is defined by two things. It's defined by magnitude. So how hard did you push it, essentially? Okay, that's also defined by a direction. Whereabouts did it go? Okay, you can consider this as some type of arrow in space. Arrow in space, and it tells us how far you've pushed a certain object, in what type of direction. Okay. In multivariable calculus, we are going to denote this with a bit of notation, and I just want to introduce some. Okay, so for example, if we call this P here, then B. Okay, so for notation, vectors can be denoted as, so let's say P is equal to this bracket here, A, B. If you have this bracket over here, like this sharp bracket, it generally denotes that's coming from some type of origin towards uh, the point, okay? If I was to write A, B, this, similar to what we did in maybe high school, this denotes a point in space, so A, B, but then having this sign over here means that you're going from one point to the other point in the A, B direction. Okay. This will get more clear as we go through more examples, but hopefully that's a good start. Another way you can denote this, particularly in 2D, you can write this as AI with a little vector sign here, plus BJ. Okay. I and J are basis vectors, and they represent 1, 0. So this is I equals 1, 0 in the x-axis, and then J would be the equivalent of O1. Okay, so essentially you're moving A times 1, 0 in the x direction, and then B times J, O1 in the upwards direction. Okay, if we wanted to bring this into a three-dimensional vector, so for example, let's call this A, B, C, okay, then the equivalent would be Q is equal to AI plus BJ plus CK, okay? Again, little vectors over here. Again, these are called your basis vectors, okay? And this is equivalent to having brackets, okay? So if you ever see them, either of them in a textbook, just know that they both mean the same thing, okay? So another way you can think of vectors is it is the shift between 2 points, like I mentioned before. But to put this in a little bit more of a general form, so let's say you have a point P1, okay? You have a point P2, okay? And you're going in this direction. So note the direction here, okay? Because that will be very important, okay? So the vector from P1 to P2, so let's write that P1 to P2, and then you write a little arrow up the top here. So you're going from P1 and you're going to P2, okay? And that is equal to, okay, well, before I go into that, let P1 equal, so P1 at the moment is a point, so P1 would equal to AB, and let's call P2 is equal to CD. Very creative names, I know. So, so P1 going to P2 would equal to the vector, okay, would equal to the x component here. So the second one, so C minus A, and then this would be D minus B. Oh, whoops. D minus B. Okay. This makes sense because you're going from the, I guess, the final position minus the initial position will give you the direction from the first to the last position. Okay. But this is the general order you want to think of when you're thinking of vectors. Okay. So let's go into some rules about vectors now. So rules of vectors. Okay. So if there's one thing that I really want you to take away from this is that vectors is merely a shift from one point to another, and it has a direction and it has a magnitude. Okay. Uh, some rules of vectors to begin with. Okay. So if I draw a little graph here, if I have this vector over here, let's call that V1. Now I have a vector here called V2. Okay. Then let's let V1. No, sorry, let me call this U. This would make a little bit more sense. And this can be V. Cool, great. Okay, let V equal V1, V2, and U is equal to U1, U2. Okay. First rule is the summation, is adding vectors. Okay, sum. The sum of V plus U is equal to component-wise. So the X values are added together, and then the Y values added together. So in this case, it'd be V1 plus U1, and then it'd be V2 plus U2. Okay. Sorry, that's the wrong bracket. That should be the sharp one over here. So apologies for that. And essentially what this looks like, if we look at this graph here, okay, so V plus U. So let's start with the V unit first. Okay, so V, and then if you add on the U vector, so this U vector here, okay, is going roughly in this direction, like this. So we go from V, okay, V, and then you add on the U vector, and the resultant vector will be this, okay? So this ends up being V plus U, okay? So that red line is that final result. You can think of summation or adding two vectors as two shifts. So you're starting from this point, okay? You shift it V ways, and then you shift it from this position to the U way, okay? And that ends up being V plus U. Awesome. Cool. Hopefully that makes sense. If we go over number two now, this would be what the opposite of sum would be subtract. Okay. This is essentially the same as sum, but if I was to go, for example, V minus U, okay, the way I like to think about it is V plus minus U, okay, which is equal to same thing. You still go component wise. So this goes at V1 minus U1, and then this goes V2 minus U2. Okay. Now, if we look at it geometrically now, okay, so it would be V. So if we look over here, it'd be V plus minus U, okay? If we look at minus U would look like, so if where U is over here, then minus U would go in the opposite direction, would go over here, okay? Now we go V minus U, which would be V, and then minus that same vector over here, okay? And then you get a line which looks like that, okay? So this is also equivalent to if you were just to put it over here. So you can think of V minus U as the line between the two vectors if they were coming from one point, okay? So this almost makes a triangle. It's like the third side of a triangle, okay? So V minus U, okay? Also note the direction as well. Whatever starts first is the direction of the arrow. So for example, if this is V minus U, then because this is V minus U, the arrow is going towards V because V is the first one, okay? Hopefully that makes sense, but we'll move on to the next one. The next one, it should be a little bit easier, and it is just scalar multiplication. Scalar multiplication. Okay, I'll probably draw another graph, but let's say we got V. Let's say K, V, where k is some real number, okay, uh, is equal to, so if we know what the v vector is, it's v1, v2. So then kv1, kv is equal to the k value times v1, and then k value times v2. Okay, so essentially you're multiplying whatever this number is, could be 1, 2, 3, 4, times whatever components you have in that vector. For example, if I draw another graph here, this should be nice and easy. Cool. So let's call this vector, let's call this v over here, and let's call it, there's a terrible graph, but let's call this 1 and 2. Okay, so v is a point 1, 2, but the vector is 1, 2 as well. Okay, so if we let k equal to, let's say 2, then the resulting vector will be 2 times 1, which is 2, and then 2 times 2, which is 4. So essentially you're doubling this line over here. Okay, and that ends up being kv, which is equal to 2 and 4. Okay, awesome. Let's go into the next point now. Let's go into the fourth thing, which is the length of the vector. Length of the vector. Okay, so the length of the vector is given by Pythagoras theorem. So if I have another vector, let's call this, what's a nice easy one? So let's call this vector 1 and 1. How, I guess a bit of a rhetorical question is, how would we find the length of this vector? Okay, I think the most straightforward way here would be just to draw a triangle here. We know that this is 1, we know that this is 1, then you can do something simply as the Pythagoras theorem. If we remember this, c squared equals a squared plus b squared. So in this case, you add the two sides up over here. So that's 1 squared plus 1 squared, which is equal to 2. And then to find what the length of this, which is c, then c would equal to square root 2. Okay, so the length of the vector would therefore be given as, so it's denoted by 2 lines here, v, but sometimes I'll get very lazy and just write 1 line each, which is the same thing, essentially. So the length of the vector is equal to square root of v1 squared plus v2 squared. Okay, so this is essentially how long one side is plus how long the other side is, square root. It's exactly the same principle as Pythagoras theorem. Okay, so we've got the length of the vector, which is great. This is also true in higher dimensions too. Okay, so if we let u equal to, let's say, u1, u2, u3, u4. Okay, so 4 dimensions where u is within the real plane and is in 4 dimensions. Okay, then the length of u is equal to u1 squared plus u2 squared plus u3 squared plus u4 squared. Okay, so this stays consistent in higher dimensions as well. Very important to know as you go into higher dimensions. Okay, now the final thing I wanted to bring up with vectors is unit vectors. Okay, the reason we care about unit vectors, so what a unit vector is, it's a vector which has a length of 1. Okay, the purpose of this is because we know that vectors come with magnitude, so how big it is, how long it is, and also the direction. Sometimes to make our life a lot easier, we just care about direction, so we don't really want the magnitude. This makes it a lot easier when you want to like differentiate something or you want to like just see what the direction of the vector is. You find the unit vector instead. So to do so, the unit vector, let me denote that as let me call it x because I'm a bit lazy with this one. So x is equal to, we're talking about v here, divided by the length of v. Okay, so let's say let v is equal to, what's an easy Pythagoras one? Let's go 3 and 4. Okay. Sorry, I keep getting the brackets not well. Okay, cool. So let's call the vector 3 and 4. Then the unit vector x is equal to, well, is equal to 3 and 4 divided by the length of v. Okay, so before we use this formula, let's find what the length of v is. The length of v is equal to square root of 3 squared plus 4 squared, okay, which is equal to square root 9 plus 16, which is square root 25, which is then equal to 5, okay? So essentially what this will give us is 1 on 5, and then the vector 3, 4, okay? So that's a unit vector. Essentially, we're just descaling, so unstretching, I guess you could say, a vector. So if I call this uh, 3, 4 here, okay, then the unit vector will be, what, 3, somewhere over here, okay, and that's x, and this would be v, okay, so you're scaling it down over here. Cool. Hopefully there's no questions there. There are 5 main things that we want to talk about for vectors. It's adding, okay? So you're summating the vectors. So if we go from v plus u, you're adding the vector from v to, and then you add on the vector u, and then you get that one long line here. Subtraction is, I'd like everyone to think of it as between 2 vectors. So if you got a vector v and you got a vector u, then it is the vector in between them, and it's going towards the first vector that you see. Okay. The next bit is scalar multiplication, which is stretching out the vector by whatever the value of k is. If k is 2, then you're doubling the length of the vector, which goes on to the next point, which is the length of the vector, which is essentially just Pythagoras' theorem onto the vector, excuse my burping, and then unit vector, where you're trying to just bring it down to a length of 1. Cool. Awesome. So that's vectors. That's a lot of rules to remember, but I'm sure it's relatively straightforward. If we go into the next point now, let's go into dot products. Dot products. So a dot product has a lot of definitions, but what it does is it brings in 2 or more vectors. So it brings in 2 vectors. So the input is 2 vectors, okay? And you know how vectors have multiple components. What it spits out and what the output is it outputs one scalar number. So I keep saying scalar, but I didn't explain it. Scalar is just essentially just one number. It doesn't have a particular direction. It just gives you like 3, 4, 5, 6, 7. Like it just gives you one number. Okay. The proper definition for dot product here. Okay. So if we let u equal to this vector, u1, u2, and then let's let v equal to v1, v2, then u dot v, okay, this is also called the inner product if you wanted to, so I might write that down as inner product, is equal to the components multiplied by each other. So the x component of u is u1, and then x component of v is v1, so it ends up being u1, v1, so you multiply them together, plus u2, v2. Okay, so essentially it's just component-wise multiplication. If you think about the other one, so this is dot product, it's a very fancy word, but essentially like with summation, it was just component-wise adding. With subtraction, it was component-wise subtraction, and dot product is component-wise multiplication. That's how I like to think of it. Okay, so I think one thing I want everyone to think about is this looks really useful. So if I think about a question, what would u dot u equal to? Let u equal to this vector. U dot u would equal to, again, it's just the components multiplied by each other, right? So if I just write it down, really spell it out a bit more, dot u1, u2, okay? Again, it is just the x values multiplied together. So u1 plus u2, u2, okay? Which is equal to u1 squared plus u2 squared. What does that look like? That kind of looks like the length, hey? Because if we have a look at the length of a vector is equal to the x squared plus y squared, okay? So this is essentially u squared, okay? Squared to get rid of the square root, okay? Hopefully that makes sense. And this is very important when we start manipulating our vectors a little bit more. Okay, particularly when it comes to the next point, which is the orthogonal projection. So I wanted to introduce a new theorem here. Okay, so new theorem, and this is incredibly important because it relates the angle between vectors. It relates the angle between the vectors and also the length of the vectors as well. So the theory is the dot product UV is equal to the length, oh my goodness, is equal to the length of U, okay, I'll write this one properly, times the length of V cosine theta, okay, where theta is the angle between the two vectors. Okay, cool. If I were to draw this, so this is the XY axis, Y axis, okay, and then let's call this V, okay, and let's call this U, okay, and from what we remember, okay, this would be U minus V, okay, because you're going from U subtracting the value of V, which therefore gives us an arrow that goes towards U, okay, remember it's always the first one, the arrow goes towards. Cool, and then if we denote this one as theta, okay, we're going to call this the proof. Okay, cool. So when we see this theorem, we see a couple of lengths. So the length of U, the length of V, this dot product here, which we don't really know too much about, and then cosine theta. What this should ring a bell is if we remember from high school maths, so let's call this high school maths. If I gave you a triangle, okay, this is A, B, and C, and this is theta, there is a rule called the cosine rule. So, which was given by c squared is equal to a squared plus b squared minus 2ab cos theta. Again, I'm just gonna have to ask you to just accept that for now. That was something that we learned back in the day. But if you want me to, I can prove this for you guys. But for now, I will just get you guys to accept that this is true for triangles. Okay, so how can we relate this triangle to vectors? Because it looks very similar, but it isn't quite the same. Okay. So in our case, over here, c squared is the length of c. Okay. So it is the length of this side over here. So it is the length of u minus v. Okay. And that is equal to the length of a. So length of v here. Okay. And then squared plus the length of b, which in this case is the length of u, okay, minus 2 length of v, and then length of u cosine theta. Cool. All right. So what we'll do now then is let's prove it. Let's prove that this is true. Okay. That's what we're required to prove right now. Awesome. So we've got this beginning step over here. So let me section it off. Okay. So if we look at u minus v, oh, sorry, I've got the squared here. Okay. So the u minus v here. Okay. So if we let u equals u1, u2, and v equals v1, v2, then u minus v would be u1 minus v1 squared plus v, sorry, whoops, u2 minus v2 squared. Okay, and because this is the length, so it's the length of these two subtracted, okay, square root, but then you square everything, okay, and then which is equal to the length of v, which is given by v1 squared plus v2 squared plus u, which is oh my goodness, u squared plus u2 squared minus, and we're just going to leave this. So 2v u cosine theta. Generally speaking, you want to put two lines here because that is indicative of length, and this could be misconstrued as absolute value. But for now, I'm just a little bit lazy. So what we'll do now, so this is fine. So left-hand side, if we have a look at the left-hand side, if we open up all the brackets, okay, so then u1 squared minus 2u1 v1 plus v1 squared. Okay, so that's the first bracket, and then we open up the second one, so u2 squared minus 2u2 v2 plus v2 squared is equal to the right-hand side. Okay, so is equal to whatever this is. Actually, you know what? I should write it down. I'm getting a bit lazy. Cool. So v1 squared plus v2 squared plus u1 squared plus u2 squared minus 2vu cosine theta. Okay, so I'll get rid of that. Okay, great. So what we can see from the left-hand side, right-hand side, we can collect some like terms. So let's get rid of the v1 squared, v1 squared, v2 squared, all the squares. So squared, 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 and then you're left with minus 2. I shouldn't skip a step here. u1 v1 minus 2 u2 v2, which is equal to minus 2 v u cos theta. And now that's really looking like something we need to prove, isn't it? So this is equal to this. That's looking really, really, really close right now. And then we get, so let's take out the minus 2 here. Minus 2 u1 v1 plus u2 v2 is equal to minus 2 vu cos theta. Okay, cool. And knowing what a dot product is, this is essentially u dot v, right? Because then it is the x component of v and x component of u, u1 v1 plus u2 v2. Okay, and then we can cancel out the minuses too. Okay, so then we get u dot v is equal to v u cos theta, which is as required. Okay, and that is the theorem. Perfect. So that's proving the first theorem. I guess the one thing that we have to assume is this one, which I can get you guys to prove maybe at home by yourselves, but if you need any help, just let me know, and I can prove that for you if you like. Okay, but that is something that we learned previously. Okay, so what are some thoughts about this? So this theorem is really good, right? Like you've got it relates dot product with the length of the vector, the angle between the vector. Okay, so just some thoughts about this. So what if u dot v is equal to 0? Okay, I'm just going to give us a quick second to think about this one. U dot v is equal to 0. If I sub that back into this equation over here, so 0 would equal to v u cosine theta. What would this mean? It would mean that either one of the vectors is literally a 0 vector, or, so this could be 0, this could be 0, or cosine theta would equal to 0. More than likely, cosine theta is going to be 0, because if the vector was actually 0, you wouldn't really care about it. But if cosine theta was equal to 0, then that would let us know that cos theta is equal to 0, then the theta would equal to pi on 2. That means that if two vectors, so if the dot product of two vectors is equal to 0, then u is perpendicular to v, because it's pi on 2, which is 90 degrees from each other. Okay, and that's a very, very important relationship between two vectors given by this theory. Okay, now what if u dot v is equal to the length of each other? Then that just lets us know that cos theta is equal to 0, so theta is equal to 0. Okay, so that means u and v are collinear. Okay, so they lie on the straight line. So let's say this is v, then let's say u is somewhere in between. So they both lie on the same vector. Cool. Awesome. I think the other point I want to bring up is that this formula gives us the Cauchy-Schwarz inequality. Okay, and what it tells us is the u dot v, so the total value, so this absolute value of this is going to be less than or equal to the length of u v. And this is purely because cosine theta, given in the original equation over here, okay, is going to be less than or equal to 1, less than or equal to minus the 1. The way I think about, just on a side note, so the way I think about trigonomic functions is, oh my goodness, is how it looks like on a XY plane. So it looks something like this. Cool. And we know that it won't go past 1, and we know it won't go past -1. Okay. And because it won't go past 1, so it won't be doubled or anything like that. So this dot product will always be less than the absolute value of the lengths here. This inequality is important when you need to prove certain facts. For example, the triangle inequality. The triangle inequality essentially states that the sum of two sides, A, B, is always going to be bigger than this side over here. Let's call this A plus B. Vector notation. Oh, no, let's not call it that. Let's call it C. Okay. So to put it a little bit more simply, then A plus B, which is the summation vector, is going to be less than or equal to A plus B. Okay. We won't prove that now, but we need this inequality to prove this inequality. Okay. And this inequality is very important when you're doing just basic calculus and doing squeeze theorems and stuff like that. And it's also very important for other geometric interpretations. So cool. So just to summarize, okay. The first theorem that we learned today for dot products is this theorem over here. The dot product between two vectors is equal to the length of these two vectors and then the angle between them. Okay. And what this tells us is it gives us a relationship between the angle. So it gives us the relationship between the angle of between the two vectors and the length of the two vectors. So if the two dot products are equal to 0, then they are orthogonal. And I should really highlight this one. Okay. So if the dot product is 0, then the two vectors are perpendicular. Cool. Very important. So let's go on to the next topic now. Orthogonal projection. Great. So orthogonal projection is if we have two vectors, so let's call this V and let's call this B. So we've got two separate vectors. The projection, orthogonal projection is the projection of V in the B direction. Okay, so how far up B does V go? Okay, and this is denoted by a vector W. This would be great for example, if you're in a ramp question in physics, okay, and you wanted to know certain forces that go in certain directions, particularly if you want to go into like the B direction, then this would be a good use for it, okay? So the formula, normally I'd like to derive it, but the formula here, I'll start off with, formula is equal to projection of onto B V. Okay, so how projection of V onto B. And that is equal to V dot B over B squared B vector. Okay. Another way you can think of it is because W lies on the vector B, you can also just call it some sort of constant B as well. But we want to show, but in the next step here, we are going to try and prove this formula. Okay. So how do we prove that this W is equal to this formula? Okay, so let's just do some notation first. Okay, so let's call W is equal to projection of VB. Okay, cool. And then if we remember from our theorem above, okay, so the theorem that we had, it's slightly modified version, but essentially I just moved it across, is cosine theta is equal to U dot V over UV. Okay, and this formula comes from the original formula here. I just moved the VU down here to get the cosine theta. Okay, so it is just the same formula. Okay, so if knowing this formula, okay, so then we know that cosine theta is also equal to V dot B, okay, over VB. Okay, and that should make sense because we're looking at this angle over here, okay? And the angle between these two is these two vectors over the length of these two vectors, okay? Cool. So the next bit we want to look at is looking at this triangle here. So if we look at this triangle here, so the VW triangle, if we remember our general rules, if our general rules of trigonometry, cosine theta is equal to the adjacent over hypotenuse, so then that would be the length of W over the length of V. Okay, so you could say that the length of W is equal to V cosine theta. Now, if we go back to this formula, okay, we can also get something similar. So we can get V cosine theta. We move this V over to the side is equal to V dot B over B. Okay, but we also, so we know V cos theta is equal to the value of W as well, the length of W. Okay, so we could essentially just say that W is equal to V dot B, B here. Okay, I'm just double checking if that's correct. Cool, great. Now the next thing I want to have a look at is, since we also mentioned that W is also equal to KB, okay, and the absolute value, so the length of W is also equal to the length of KB, okay, which is equal to K length of B, okay? So now that we know that W is equal to KB, we're trying to find what K is. So then this, so we move this all the way over here. So then KB is equal to V dot B over B, okay? So then K is equal to V dot B over B squared, okay? So we've got this value over here, okay? Now, since we know that W is equal to KB, then we substitute this back into here. So W, which is equal to the projection of V onto B, is equal to K, which is V dot B over B squared times this. Okay, so this is kind of messy, but in terms of the proof, okay, what we are trying to do here is we use the theorem to find the angle between V and B, and then we use the angle theta using basic trigonometry over here. So I should draw this. This is the trig part. This is the new part, so the theorem part. Okay, and then we combine them together with this third part. Okay, and this is the length of W. Okay, so that's three parts here. And then what we're trying to do is, because we know that the length of W is some constant times the vector of B, then we're trying to solve for this constant over here. We put it back into this formula here, which we found by combining these two, okay, to find what K is. We know what K is now, okay, because we moved this B down over here, and then we found what W is, and then therefore that is the final proof, okay, as required. Super complicated, and you'll probably never have to prove that, okay? But it's good to know that it's not just some formula that came out of thin air, okay? Cool. So that's orthogonal projection. The final part for today will be cross product. Cross product, okay? Fantastic. Cool. So the cross product is a special formula that only works in 3 dimensions. Okay, 3 dimensions, and where V is in the real plane in 3 dimensions. So essentially it's 3 dimensions, but to put it in a more mathematical way, it lies, there's like a backwards E, okay, lies in the real plane in 3 dimensions, okay? And it is defined by, if we let U is equal to U1, U2, U3, because 3 dimensions means there's 3 components to it. Okay, I probably should have emphasized that to begin with. And then V is equal to V1, V2, V3, okay? Then the cross product, which is denoted by U times V, is equal to I, J, K, which is the basis vectors of the 3 dimensional plane. U1, U2, U3, V1, V2, V3. Okay, so this is a determinant, not a length. Okay, if we remember from linear algebra, if you have done linear algebra, um, let's do a bit of a quick mini revision of this. So determinant. To find the determinant of a matrix, determinant, okay, let's call the determinant of, let's call A, this is a 2 by 2 matrix, 2 by 2, so it has two rows, two columns. Let's call this 1, 2, 3, 4. To find the determinant of a 2 by 2 matrix, you multiply these two together, and then you multiply these two together, and you subtract it, okay? So then this is equal to 1 times 4 minus 3 times 2, okay? Which ends up being what? 4 minus 6, which equals 2. Okay, so that's a 2 by 2. For a 3 by 3, okay, let's call A is equal to A, B, C, D, E, F, G, H, I. Okay, that's, and then the determinant would therefore be this. Okay, that is equal to, I'll just give you the formula, A, and then times the determinant of E, F, H, I. Okay, which is essentially, if you look at A, then you get rid of the first row, first column, and you just look at the bottom corner here. Okay, minus B, and then if we're on B, then you get rid of the second row, second column, first row, and you get D, F, G, I, D, F, G, I. Okay, and then plus C, so positive minus positive, C, and then you look at C here, then you get rid of the third column, first row, then you look at this square over here, and then you find the determinant of D, E, G, H. Okay, cool. So if we go back to our example over here, then U cross V. So I should also say that U cross product produces a vector which is perpendicular, is orthogonal, sorry, orthogonal to U and V. Okay, so if you can imagine, if you've got, let's say X, Z, sorry, this should be Y. Okay, and let's call this X. Okay, let's say you've got one vector here, you got another vector here, then you've got a third vector, which kind of looks like this, which is orthogonal to both vectors. Wow, that is a terrible 90-degree sign. But by solving this, this is how you get that third vector. Let's call this, if this is U, this is V, let's call this X. Okay. Oh no, maybe let's not call that X, let's call that A. Okay, cool. So that's what the cross product is. Okay. Uh, interestingly, the cross product, so I'll get you guys to compute this in a question. I won't show you how to compute it for now, but I just wanted to go through probably more interesting things with the cross product. So the area of a parallelogram, which is spanned by gram, which is spanned by vector AB. So let's say I've got a vector here and I've got another vector here. Okay, area of the parallelogram, let's call this A, let's call this B, is given by A cross B. Okay, so the area of this parallelogram, this is given by A cross B. The magnitude of A cross B, which is the length of A cross B, which is also given by A B sine theta. Okay, so I think a good question is, why is this the case? And while I won't formally prove it, I think a good example is if we have, let's say we're on the XY plane. And I did mention that the cross product only works in 3 dimensions, so we will give these all 3 components. But let's call this B, and let's give it values B1, B2, and 0. Okay, and let's call this A, and this is given values of A1, 0, and 0. Okay, so there's no Z value at all, but there is a there's no Y value, but there is a X value, and then this is B over here. So let's call this theta. Okay, then the area of this parallelogram would look something like that. Okay, and I'm just going to note this over here. So let's solve for the cross product of A and B. Okay, so A cross B is equal to, let's say, I, J, K, and then B1, B2. Oh no, sorry, I should do it in order. So A is A1, 0, 0, and then B is B1, B2, and 0. Okay. So that should be a determinant. My bad. Okay. And that is equal to, okay, if we remember our cross product formula, so I, and then we find the determinant of this, okay, 0 times 0 minus 0, which is 0, okay. And then we find J, so minus J, okay. And then we look at A1 times 0, B1 times 0, which is 0, okay. And then plus K, and then if we look at uh, these four, then we get A1 times B2, which is A1 B2, okay, minus B1 times 0, which is 0, okay. If we find the length of A cross B, this then gives us square root of 0 squared plus 0 squared, because length of this x component, length of y component, and length of z component, plus A1 B2 squared, which is essentially just A1 B2. Okay, so we know what the cross product here of A cross B. Okay, great. Now, if we were to actually find uh, the height of this area of the parallelogram, so if I just redraw this over here, great. Okay, so we know that this here is A1. Okay, 0, 0. So the length of A is therefore equal to A1. Okay, so this is A1. Now we want the height of this as well, because the area of a parallelogram is given by the base times height, and we know what the base is A1. This is theta. Okay. But in our case, because B is B1, B2, 0, we know that this height is B2. Okay. So then we know that the area of this is therefore, so area is equal to the base, which is A1 times B2, which is A1 B2, which is also equal to the cross product of A cross B. Okay, so this is a very oversimplified example, but it was a good example to show that this is actually true. So the cross product is equal to the area of the parallelogram. Okay, cool. Hopefully that convinces you at all. And if that doesn't make sense, please just reach out. Okay, now some of the more mundane things. Okay, I just want to go through some properties. Properties of dot and cross product. Cool. Properties of, okay. And I'm just going to zoom through these. I'm not going to prove these ones, but they should look somewhat familiar. Okay. So if I give U times V plus W, and all three of these are vectors, then this is the distributive law, and this will give us U times V plus U cross W. Okay. And this is called the distributive law. Okay, and this is also true for dot products. So if you replace the cross with a dot instead, dot instead, dot instead, it's also still true. Okay, for the cross product, if you do U cross U is equal to 0, then that means the two vectors are collinear. Okay, so sorry, probably a better example is U times V is equal to 0, then U is collinear with V. Okay, cool. And the final bit, which I think is just a fun little thing, is uh, triple scalar product. Product. Okay, and this is uh, U dot V times W, oh, which is equal to the determinant of U1, U2, U3, V1, V2, V3, and then W1, W2, W3. I won't prove this one, but this is equal to the area for parallelepiped. I definitely mispronounced that, and I definitely misspelt that. But essentially, what it is if you have it's the area, it's the volume. So let me draw something. Y, Z, Z. Okay, this is X. Okay, if you have like let's say this vector over here, this vector over here, this vector over here, then the volume of, oh, this is so gross. But for example, the volume of this volume over here, which is covered by these three vectors, is determined by this formula over here. That is a terrible drawing. However, I will fix that up. It may be another time. Cool. So what I'll do now is I'm just going to copy and paste some example questions onto this lecture, okay? And I would like everyone to just give it a go if you have the time, okay, to just reinforce the learnings that we had today. So if I pop this over here, good example questions. All of these are mostly derived from Anton, or I've mixed it up with some of my own numbers, okay? If I dot product over this, orthogonal projection. Cool, perfect. And then cross product at the end. So this is just to reinforce some of the learning that we did today. And now let's just review what we've learned as well. So cool. What I'll do is I'll link this as a link in my YouTube, okay? And you can just review this later, okay? But let's review what we've learned so far. So that's a lot. Let's zoom out a little bit. Cool. So what we went through today is vectors, and we know that vectors is built up of a magnitude and a direction, and essentially it's just a shift from one point to another, okay? And this is denoted from a point, an arrow in space. Because it's a shift from one point to another, you can subtract 2 points, okay, to give you that vector, okay? It can be denoted with arrows over here. It could be denoted with I and J, which are the basis vectors, okay? And these are synonymous to each other, so they mean the same thing. The second part is we learned some rules about vectors. So adding vectors. So if you go v plus u, so you move the point from this point to v, and from v to u, okay, we'll give you v plus u. Subtracting will give you the vector which is between the two vectors, okay, and it goes towards the first one. You can think of it as going from one vector, subtracting the other vector as well. Scalar multiplication, which is just stretching the vector, the length of the vector, which is just Pythagoras theorem, and then unit vector, which is just the vector divided by the length of the vector. Okay, this is very important for things later on, okay, when we don't want to care about magnitude and we only care about direction. Then the next part we looked at is dot products, or also known as inner product, and is essentially just component-wise multiplication. So the x values here multiplied plus the y values multiplied. And it's relevant because it gives us connection between the angle between the two vectors as well as the length of the two vectors. Another thinker is if you were to dot product itself, it gives you the squared of the length. And this is a very useful application when we need to prove something in the future. Okay, so make sure you remember that. The dot product of itself is the squared of its length. Okay, and then we prove the formula, which with the cosine rule, which is great. And then we know another key point is that if two vectors dot product is equal to 0, then they are orthogonal to each other, or they are perpendicular to each other. Okay. With this theorem, you also get the Cauchy-Schwarz inequality because cosine can't be bigger than 1 or less than -1. So the absolute value of a dot product is always going to be less than the length of the two sides. Okay. Then we talked about orthogonal projection, which is just a vector projecting onto another vector. Okay, so how far in the b direction did v go? Okay, which gives you w, and then we proved it. Essentially, you just need to memorize the formula, but it's good to know how to find this projection. Okay, and it has strong applications in physics as well. Okay, it's also great for finding out a distance from a point to a plane, which we'll talk about in the future as well. The next point we talked about was the cross product. Okay, so with the cross product, you are trying to produce a vector which is orthogonal to both u and v are orthogonal to two other vectors, and it's given by the determinant with the basis vectors in the first row, one vector, one vector. Okay, and this gives you a vector which is perpendicular to both vectors. The other thing with the cross product is that it's also the area of the parallelogram. Okay, and we've casually proved it here. Okay, but the area of the parallelogram, which is spanned between the two vectors, so which is in between the two vectors, is given by A cross B. Some properties are the distributive law. Okay, so essentially same as if you're doing regular algebra. If you got two cross products which are equal to 0, then you get that the two vectors are collinear, which essentially means that they are lying on the same line with each other. And then you also have the triple scalar product, which is with this terrible drawing, it gives you the volume. Sorry, I shouldn't say area, but the volume of the parallelepiped. So it's a parallelogram, a 3D parallelogram. Oh man, I should really know how to pronounce that. Okay, cool. And then some example questions here. A lot of these are just reinforcing what we've learned. So for example, the first one, find a vector of length 2 that makes a 45-degree angle with positive x-axis. What I would recommend is just drawing something like this, makes a 45-degree angle. So this is pi on 4. Okay, this is length 2. Okay, give me what the vector is. Okay, if this length is 2, this is 45 degrees. You can use SOHCAHTOA, you can use trigonometry to figure this one out. Okay, then you've got the unit vector, you've got opposite directions, half the length, all this kind of good stuff. Okay, if there are any questions, just reach out on my YouTube, and then we can I can send you an email if you need to, so we can solve this out together. Thank you, and have fun doing these exercises. Thank you so much.